Let's talk about lines in R2. We know that ax plus by plus c is the equation of a line. You're often used to seeing the c on the other side. It doesn't really matter where you put it. Believe it or not, it's actually better to put it this way, to have the 0 over here. That way all of the constants and all of the variables are on one side and the 0 is over on this side, because this idea of homogeneous systems is going to be very, very important for us, because remember we discussed homogeneous systems and the conditions under which a homogeneous system has a solution where the determinant of the particular matrix, the coefficient matrix, is equal to 0 and things like that. So it's often best to write it this way, and it's more consistent when you move on to planes and equations of things called hyperplanes in n-space, which are just the analogs of lines and planes in the spaces that you know, R2 and R3. Okay, well, if I have some point P is xy, and I have, actually this is P1, so x1, y1, and if I have a point P2, which is x2, y2, well, if these 2 points are on that line, then they satisfy the following. You basically just put the x1, y1 in for x and y, so you get ax1 plus by1 plus c equals 0. Actually, I don't need that c1 because c is constant. And I have a times x2 plus b times y2 plus c equals 0. So these 2 points satisfy, if they're on that line, they satisfy this relation, right? Well, let's write all three. Let's write the generic version and these one on top of the other. So we have ax plus by plus c equals 0, ax1 plus by1 plus c equals 0, a x2 plus by2 plus c equals 0. And now take a look at this. This is a system. It has, we have 3 equations. We have 2 unknowns, x and y. We have some coefficients. We have, let me highlight these in red. We have a, we have b, c, a, b, c, a, b, c. And then we have the x, the x1, x2. We have the y2, the y1, and the y. We can actually write this as a matrix times a vector. So what we're looking for here are the a, the b, and the c. So these x's and y's are actually the things that become the coefficients, and the coefficient in front of the c is the 1. So let me rewrite this in matrix form as, let me actually do it this way. X, y, 1, that's this, this, and the coefficient here is 1. x1, y1, 1. x2, y2, 1. This is our matrix. And then multiplied by the a, the b, and the c. So the a, b, and c are the 3 numbers that we're actually looking for, and that's equal to, well, 0, 0, 0. Again, it's 0 on the right. So this is a homogeneous system. This is a homogeneous system, and this is the matrix representation. So given 2 points and this equation that we know, we can set up this homogeneous system, and now we know how to solve this. As it turns out, so these are numbers, these are actual numbers. These x and y, they stay as variables. That's why they have no subscript. So because this is a 3 by 3, it's an n by n, and it's a homogeneous system, we know that it has a solution, a non-trivial solution, if the determinant of this matrix is equal to 0. That's one of our theorems from some lessons past. So let's go ahead and set up this determinant. Now let me actually write that down specifically. So the determinant of, in this case, let's call the matrix A, equal to 0, it implies that there exists a solution. In other words, A, B, C can be found. They represent actual numbers. Well, so the symbol for determinant is that straight line, x, y, 1, x1, y1, 1, x2, y2, 1, we want the determinant to be equal to 0. So let's expand the determinant and come up with some equation, conditions on x and y, such that this is satisfied. Okay, so let's go ahead and expand. We're going to expand, of course, because x and y are variables. We're going to expand along that row, okay? So I take my, let me actually do this in blue here. So I'm going to knock that out. So what I end up with is x times let me see. You know what? Let's do this a little bit differently. Let's actually stop here. And since we're dealing with x and y, when we actually do some numbers in here, then we'll do the expansion. So again, you're going to expand along the first row, but this is what's going on here. So when you have 2 points, x1, y1, x2, y2, you can set up this matrix, solve for the determinant, and you'll actually get your equation of your particular line, which is the original line that we were looking for. So let's actually do an example.